Hello everyone. Now we are studying the unit current electricity. Before going to start today's class regarding Wheatstone bridge, we have to focus whatever we learned in the previous classes. Till now we have studied about current, drift velocity, Ohm's law, Kirchhoff's laws. In that Kirchhoff's current law, Kirchhoff's voltage law, we have studied in detail. Today we are going to focus on Wheatstone bridge. In this, we have to use Kirchhoff's current law as well as Kirchhoff's voltage. Now, you must just focus on revision of Kirchhoff's current law. What it states, at any junction in the electrical network, the algebraic sum of incoming current and outgoing current is always equal to 0. Or at any particular junction, the sum of incoming current is equal to sum of outgoing current. In simple. And what Kirchhoff's voltage law states? According to Kirchhoff's voltage law or Kirchhoff's loop rule, we can state that the algebraic sum of EMF and the product of current and resistance in the network is always equal to 0. With this basic information, today we are going to study Wheatstone's bridge. What are the key points we have studied in this class? Initially we have to study the construction of Wheatstone bridge. Then we have to study or we have to derive the balancing condition for the Wheatstone network. Then we have to see some numerical which are based on this Wheatstone bridge. Now here, before we focus on the construction of this Wheatstone bridge, what compounds we need to construct this network? We need 4 resistances, P, Q, R and S. Out of these 4 resistances, 3 resistances must be known resistances and 1 resistance is unknown resistance. Means what is the physical significance to study the Wheatstone network? We can determine the value of unknown resistance. Similarly, we can find out the ratio of resistances. Then one more component we need here, which is the measure of current, that is galvanometer. And one battery we have to use here having EMF E. Now see here, this Wheatstone bridge network, it is just like kite. Means the patang. If the structure of this Wheatstone bridge, when we observe, it seems like a kite. Now, see here, we can give the points A, B, C and D. In between these node points, they are connected various resistances. P is connected between A and B, Q resistance is connected between B and C, S is connected between C and D, where R is connected between A and D. Now in between B and D node, we connect the galvanometer which gives the measure of current which is flowing through this circuit. And here we are connected the battery of EMF E in between the points A and C. When we connect this battery across these 2 terminals, some current will be flowing through this circuit which we are denoted by I. Now, when this current I is reached at point A, it will be divided. So, out of this I current, I1 is the current flowing through the resistance P and I2 with the resistance flowing through the resistance R. When this I1 is flowing through this resistance P and reached at this point B, again it is branched or it is divided into 2 currents. Out of that, one is Ig. Suppose the current through this Q, we can denote it by I3. Now see at this point D, this I2 and Ig, these are the incoming currents. They mix together or they adds up here, and one more current will be here which is flowing along this S resistance, that is I4. Now we can say that I1 is the current flowing through the resistance P, I2 is the resistance, I2 is the current through the resistance R, resistance Q and I4 with the current through the resistance S. Now, before going to derive the balancing condition for the Wheatstone's network in terms of these four resistances P, Q, R and S, we have to study or you have to know the balancing condition for that. Now here, the galvanometer is connected. When the current is flowing through this particular direction, it will show some deflection either to the left hand side or right hand side. But when the resistances in this arm, that is P and Q, and the resistances in another arm, R and S, they are balanced. That time, with the ratio of P by Q and the ratio of R and S is become equal, that time the current flowing through this galvanometer is equal to 0. Ig will be 0. This at balancing condition. At balancing condition. Of Wheatstone's bridge, Ig must be equal to 0. Ig must be equal to 0. Now, we have to derive the condition, balancing condition for this Wheatstone network. We have to use two laws. That is, first one is applying Kirchhoff's current law to nodes B and D. Applying Kirchhoff's current law to the nodes B and D. At node B, we have to use this junction rule or Kirchhoff's current rule. See here, at this node B, I1 is the incoming current, where Ig and I3 be the leaving currents or outgoing currents. And according to KCL, this incoming current I1 is equal to sum of outgoing currents Ig and I3. But what is our condition? Ig is equal to 0. Therefore, we can simplify this as I1 is equal to I3. We call it as equation number 1. Similarly, at node D, I2 and this Ig with the incoming currents, where I4 is the outgoing current. So, sum of these two incoming currents, that is I2 and Ig, is equal to outgoing current. So, we can write down I2 plus Ig is equal to I4. Once again we put Ig is equal to 0, therefore we will get I2 is equal to I4. This is our equation number. Now, next step, applying KVL to loop. Applying KVL to loop A, B, D, A. A, B, D, A. See the loop? A, B, D, A. Now in this loop, there is no EMF is there, only it consists of resistance and current. So here I1, it is the current flowing in the direction of traverse. Ig is the current flowing in the direction of traverse. But this I2, it is in the opposite direction. So the product of I1 and P and product of Ig and G must be negative because they are in the direction of traverse. Where the product of I2 and R, it is positive because it is in the opposite direction of the traverse. So we can write down here minus I1P minus Ig into G plus, this is in the opposite direction of the traverse, so I2 into R is equal to 0. Now we can simplify this. Minus I1P, Ig is equal to 0, so this term will be equal to 0, plus I2R is equal to 0. Therefore, we can write down I1P is equal to I2R. We call it as equation number 3. Now, we apply KVL. Applying KVL to loop. Another loop we are considering here. BC DB. Loop BC DB. BC DB. Now in this loop, when we are moving from BCDB, I3 is the current flowing in the direction of traverse, where this IG and I4 are in the opposite direction. So the product of this I3 and Q, it is negative, where the product of IG and G, I4 and S, it should be positive because they are in the opposite direction. So we can write down here minus I3Q plus I4S plus IGG is equal to 0. This current I3 is in the direction of traverse, where I4 and IG they are in the reverse direction, in the opposite direction of the traverse. Therefore, this product we have taken positive. Now we can write down I3Q plus I4S, IG is equal to 0, therefore this term will be 0. We can simplify this as I3Q is equal to I4S. Now from equation 1 and 2, I1 is equal to I3, I2 is equal to I4. So for this I3 we can write down I1Q, and for this I4 we can write down I2. Yes, we call it as equation number 4. Now the final step, divide equation 3 by 4. Divide equation 3 by 4. Divide equation 3 by 4. So 3 I1P divided by I1Q is equal to I2R divided by I2S. If you simplify this, I1 get cancelled, I2 get cancelled, we can get P by Q is equal to R by S. And this is the balancing condition of the Wheatstone's network. The ratio of the resistances P and Q is equal to the ratio of resistance R and S.